All right, lots of questions this morning. So just keep in mind, this is the only live stream this week because we're off Thursday for professional development. We're off Friday for Good Friday. Get you out. Here you go. All right, so I'm going to kind of start with the questions in no particular order. We'll start with one that got asked in the chat just because it's easy to answer. Reactions to make azo dyes. So pretty much all today's questions that came in advance were for 252. When you synthesize an azo dye, you start with some type of amine functionality, and you react it with nitrous acid, HNO2, to give you the azo complex. And this is going to couple to another aromatic ring. So let's say you have the acetylsalicylic or the salicylic acid. And you're going to couple this with the azo. And the way you're going to do this is it doesn't matter what's on the benzene ring you're coupling to. This azo group is always going to get added para to whatever all the other groups are by sheer merit of the fact it's just big. So we don't have to worry about whether or not these are ortho-meta para directors. The only thing we have to worry about is where they are relative or to where we're coupling. This is the least sterically hindered part of the molecule, and so we're going to end up having an N, benzene ring. So that's all you do for the azo lab, is that pretty much they're all this structure, with this being whatever was in the beaker that you reacted with. And again, we're going to add in para positions. So for null, we're going to add the OH group as far away as we possibly can. And for the 2-naphthol, we're going to add as far apart on the ring as we possibly can. What about the extra benzene ring attached? Not sure what you're referring to. Yeah, I'm presenting early today because I've got PD from 11 to 12, so just going to bump this up an hour. But this is the extra, I mean, the ring you're attaching is the one that connects to that, originally to the NH2 group, and you're just adding that N2 bridge to it. All right, I'm going to keep an eye on the chat, but I'm also going to bring up the first homework question. There's a lot of homework questions. First one is question 14. And it is asking for the structure of the aldol addition of pentanal. Extra ring to the NH2. No, so the azo dye is not going to couple with itself. So this is always, for all of these, we made this as the starting precursor. And this couples to a benzene ring. We're not going to concern ourselves with this coupling with itself. In principle, this could couple like this. And you could get these long polymer chains. We're just not going to worry about those. Again, all we're doing is we're coupling our starting benzene ring to whatever was in those beakers through this N2 bridge. All right, pentanal. All right, so for this reaction, it's pentanal with itself. We only have one alpha carbon. It's going to attack here. And so we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this will end up being our final product. Again, it's just asking for the aldol addition product. And let's see if there's something weird about the key. Nope, that's kind of the answer. The key's drawing it in kind of a weird way, but it will know because of the code that's backing this up, it won't really matter. But yeah, this is just the aldol addition of pentanal with itself. We only have one alpha carbon. It always attacks this aldehyde. We did the aldol addition, which is more aldol condensation. This is the more likely product. Question 16. Can the aldol addition product and an aldehyde undergo an aldol? Can the aldol addition product undergo an aldol addition? Why or why not? The reaction occurs to all the structure of the aldol product is not a reaction. The aldol addition product is. So look at the aldol addition product here. Can this undergo another aldol addition reaction? The answer is technically yes. We do have one more hydrogen here, and it should be stabilized because it's next to this ketone. So in principle, it could react to attack another one, and we'd end up getting the diol. So yes, the aldol addition in pentanol has an alpha hydrogen and therefore can undergo, and then let's make sure. I don't feel like drawing the structure. Oh, okay. So it's even asking if it's not even asking this. It's asking can even this undergo aldol addition, which is weird because that's a previous problem. I'm guessing that was the confusion. Can this undergo aldol addition? Yes, it has an alpha carbon, and it's pretty much what you drew in the previous example. So yeah, if you're a little confused by 16, it's weird because question 14 answers it and says yes because it's asking you to find the aldol addition product. Question 18. 2-ethyl 1-hexanol is widely used industrial chemical outline synthesis starting with butanol. So we want to go from this to 1-ethyl 1-hexanol. 1, 2, 3, 4, 5, 6. 2-ethyl 1-hexanol. So you start with butanol. The hydroxide here should abstract a hydrogen to give you that. Where are they going with this synthesis? Ethyl, 2-ethyl, 1-hexanol. They hydrogenate, which would imply, so there's an H2 PT step. So that would be hydrogenation, but this is weird because I think they're wrong about the name of the product. So we have 1, 2, 3, 4, 1, 2, 3. I think they have named the product incorrectly for this problem. Because I get where they're going at. This is 1, 2, 3, 4, 1, 2, 3, 4. So if we made this an alkene here, maybe they didn't name it wrong. It's a little complicated. So I'm reverse engineering the problem. So we're going to kind of cheat. We know that we're in the unit on aldol addition and condensations. So if I were to backtrack this out with H2, I could have a ketone here, alpha beta unsaturated ketone. Nope, that goes there. So 1, 2, 3, 4, 1, 2, 3, 4. So there's one butyl group and another butyl group. Excuse me. So conceivably what's going to happen when we do this hydroxide water is that we get an aldol addition product. And so if we draw our molecules, 1, 2, 3, 4, this carbon is going to attack this carbon to give us initially this product. And then what we're going to have subsequently, because we're under basic condition, is the aldol condensation, which will give us this structure here. So your first product here that you're drawing, it's not stating it explicitly, it would be better if it did, is that you're forming this aldol condensation product. This aldol condensation product you subsequently hydrogenate, so the missing reaction here is H2, it's nickel here, and this will hydrogenate this double bond and this double bond to give you 1, 2, 3, 4, 5, 6. There's your hexanol, and there's your ethyl group. Good problem. It would be better if they explicitly stated that you're going through, they would give you the hint that you're going through an aldol condensation product. But yeah, that's how you do it. It's butanol with itself, forming an aldol condensation product, then hydrogenating and get the final product. 22. In TD, I don't know if I answered your question. If not, I'm not quite understanding your question. So you can just ask it again and I'll answer it as soon as I see it. Draw the structure of the mixed aldol condensate or condensation product of benzaldehyde with cyclohexanone. So if we have cyclohexanone and benzaldehyde, and we're going to get, if we add our hydroxide, we're going to get an attack here, and with the water present, we'll end up generating at first the aldol addition product, and then it's asking you for the condensation product. So the condensation will eliminate the water from this bond, and you'll end up getting a conjugated end up getting that product. So let me check to make sure it's not asking you to do the double addition. Well, we're getting there, Dia. I've got from the question I got emailed 22, 24, 30, 33, 35, 40, 54, 68, and 73. So I got 8 more questions to work through. And then I'll get to your questions. Yes, so you end up forming this product here. Does the NH2 end up going least substituted or most substituted? So it actually goes back to the epoxide unit. So it depends on if we're on acidic or basic conditions. So we have NH3, and the question is whether we have an acid or base. If we have an acid, we'll end up going through the carbocation intermediate, and it'll end up going to the most substituted. If we're under basic conditions, it'll end up going to the least substituted. So it's just kind of back to the epoxide units. It's again, it's more for, well, I'm going to say priority over halogens as well for amine. Yes, the amine functionality definitely trumps the halogen. Halogens rank the same as alkane branches, and alkane branches, the only thing they ever beat, actually they don't beat anything. Alkane branches are the lowest ranked priority groups. What was the next question? 24. Draw the cycling of the Deichmann cyclization product formed in the treatment of the following diester with sodium methoxide, followed by acidification. I'm going to get rid of this because I don't teach Deichmann cyclization. It would be interesting though. Yes, NH3 is typically going to be under basic conditions, so yes, it would make sense to, because NH3 is its own base, you're most likely going to get it on the least substituted. But let's see if we can figure out the Deichmann cyclization. So the sodium ethoxide, okay, I should probably write up on the board first. So the reason why they're making work with sodium ethoxide, in principle, this could undergo a nucleophilic attack with that carbonyl, but we're not going to get anything for it. You're welcome. So really what this is serving is a strong base. And this strong base here is going to abstract the hydrogen from this group here. So again, the whole reason for going with ethoxide is to make sure that if it does any undesired reactions, we don't end up changing the molecule. So now you've just got an aldol addition. So 1, 2, 3, 4, 5, 6. And we'll number these 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Carbon 6 now has an alcohol hanging off of it and an ether. And carbon 1 now has this group hanging off of it with that branch hanging off. So again, we're just going to treat this as an aldol addition first. I doubt it will do condensation, but let's see what the key says. So how do you get the diketone? All right, okay. So what will happen next is that this is an acetyl. Cool. In fact, this is a hemiacetyl. And hemiacetyls will decompose under basic conditions back to the ketone. So this will end up collapsing back down and you end up with this ester ketone pair. An interesting reaction. Came across electron donating withdrawing amine. It says electron donating groups cause it to be more reactive. Does that mean it will be less stable with electron donating groups? It's not so much that it's less stable, it's just that when you add electron density to nitrogen, it makes nitrogen uses its lone pair to do its chemistry. So by adding electron density, you make its most reactive part of the atom, that lone pair, more reactive. Get the structure, including structures of the two most stable enol isomers, and use dash bonds representing hydrogen bonding in the enol. So this is just more emphasizing why these are particularly why these materials are particularly acidic. So when it says OH on the left side of the molecule, what we're going to do is get tautomerization. We're always pulling the hydrogen out here, but we can pull it off to the left, or we can pull it off to the right. Excuse me. So in terms of hydrogen bonding, this will hydrogen bond to the adjacent ketone. So this is what you're going to end up with when you're done. The hydrogen moves from here to here. Oh, sorry, forgot my double bonds. And the hydrogen bonding just goes to the adjacent oxygen. So this is what I talk about, I think, when I start talking about the microreaction in the notes. Probably the complication here is just drawing that dash bond in the structure. But yeah, there is a hydrogen bond here and here, and this ends up generating both a 6-membered ring and more or less a conjugated 6-membered ring if you look at it. So we got a double bond here, and then we can use the lone pairs on this oxygen, more or less to generate an aromatic ring. I know I'm kind of playing light loose with that definition here, but yeah, we actually get good conjugation in this type of ring. 30, 33. Give the structure of the expected organic reagent and the product of the reaction of 3-phenylpropanol with sodium hydroxide and ethanol at 10 degrees C. So this is just going to be an aldol condensation with itself. So this is going to attack here, and I'm going to guess that this is a condensation reaction. We'll do the addition product first, but most likely because you've got these basic conditions, you're going to end up generating condensation product. So 1, 2, 3, 1, 2, 3. So this would be the addition product, and then the condensation product. Would be this. You'd actually want to make it trans to kind of increase the stability. So let me look at the key. So with this one, they're just doing the aldol addition product. They're not doing the aldol condensation. I think it's a little weird, but actually you're going to end up generating this structure instead. Again, under basic conditions, I would expect you to generate the condensation product, but it's kind of asking for the addition product. 35. Give the structure of the principal product of the following reaction. And again, the reason they're going with ethoxide here, any base you put in here could react with this ester. So we want to make sure that wherever reactions do occur, they don't change the molecule. So this is just acting as a strong base to deprotonate here. This will attack that carbonyl. Now again, one of these is a hemiacetal. So what will happen is that this will pop off. We'll recover the ketone. And let's see if I'm right. By the way, you're not going to see questions this hard on the exam. This is a little does not look like a question I would have picked. I tend to believe this was just something in the pool. I mean, they're good problems. Like, I would like to work them in front of a classroom, but I think these are a little bit on the hard end because they are drawing together a lot of concepts. 40. Show the mechanism of how the starting aldehyde is converted to enol form using the following mechanism arrows. This is actually a good question to ask you to make sure you understand the mechanisms. Okay, so question got to ask, if a molecule attacks the double bond, has COH group, and the other part doesn't, instead of has a ketone with alpha carbons, what will occur? Decarboxylation or Robinson? Decarboxylation only occurs if you have a dicarboxylic acid. So that double carboxylic acid is super unstable, and basically it's just yanking too much electron density off the molecule. So unless you have both COOH groups, you're only going to get the annulation. So the mechanism for this is under acid catalyzed conditions. First attack is by the oxygen onto the hydrogen to extract the hydrogen. I'm just going to write this as a pH group. I really don't want to write it out every time. This water will abstract the hydrogen. Oh, yes. And in abstracting the hydrogen, it'll kick the bond down, kick that bond around, and we end up generating this OH. Now, let me make sure it's making, let's see how many steps it's breaking into. Correct. If you only have one, you just end up with a carboxylic acid product. It's just not, doesn't have enough electronegativity on it to really drive that decarboxylation. Yes, so it does do the big concerted mechanism for this part. So first we have extraction of hydrogen, then the water extracts the hydrogen off of the ketone, or aldehyde in this case, and forms a double bond. So yes, that's a typo in the packet. It doesn't need lights. This kind of is unique to ketones. Typically, we just have an alkane. We need free radical halogenation. But in the case of ketones, because we have that acidic alpha carbon, it will actually attack the halogens themselves. Oh, did 40, thank goodness. 54. Draw the structure of a compound that has molecular ion mass. Should speak to our. Okay, I'm going to kill this question. This was not a question I would have asked you. So we're going to toss 54. Yes, you're welcome. I mean, most of these you could work out. So you could say, well, NH2 groups have a bending mode at 3300, 3500. That's the hydrogen bonding mode. So, but I don't like that question. That's probably not what it looked like on my end when I did it. 54, 68. One 1,3-dibromo-5-nitrobenzene can be prepared by paranitroline. Outline a reasonable series of steps leading to 1,3-dibromo-nitrobenzene by filling the missing information in the diagram below. Well, that's a bad question. Why is this a bad question? So, I do not agree with what they've done in this problem. What did they do? Br2 and acetic acid. I do not agree with this question. I'll get to the slides in a bit. So why don't I agree with this question? Their claim is that the first step here is this. Not quite sure how they're getting to that. This would be a weird reaction. I'm not seeing where the hydrogens go. I'm seeing a lot of charge issues with this too. I would agree with this statement and say that yes, you could do the dibromination, and I would entirely agree with this. And then from there, they want you to go to HNO2 plus, I think it's an alcohol, to generate the, basically remove the amine. So this is just a bad question. I like the overall idea of it, but this is just not correct. Br2 acetic acid shouldn't be doing that. So we're going to kill question 68. Last one, 73. Identify the principal product of cyclohexanone with cyclohexylamine and into H2 nickel. So we're going to end up reducing whatever we're making. All right, we know we're reducing something. Okay, so this will undergo nucleophilic attack, and as a first step, we will generate this product. As a second round, because we have a hydrogen available here on the nitrogen, we'll get elimination. And on our addition of H2PT, we'll reduce this double bond, and we will get dicyclohexyl N-dicyclohexylamine. That's my guess. Yep, cool. So, happens here is we get a nucleophilic attack. This is just a reaction of amine with a ketone, and then subsequently we just lose the water. It's just a more favorable reaction, and then we reduce off that double bond with H2PT. Okay. If the hydrogen is present on the less substituted carbon, will it get removed from there only? If there is not, and only a tertiary carbon present, will it just remove it from the tertiary instead? Okay, so let's go back to your first question page. Questions page 79. Is the amide chain with carbon number 1 and the carbonyl, so the primary chain is ethamide, which is confusing because its common name is acetamide, which is what it's actually called. But yeah, I would just go with the IUPAC name as ethamide. Ethanamide was what I read in the book, but I would not put it past me typing it in wrong. Yes, it is ethanamide. I probably did it wrong in the video and called it ethamide. It's supposed to be ethanamide. So yes, it's just a mistake in the video. If you could send me a link to that video just so I can correct it this summer. Slide 89, you will form all those products. When writing the product, we include all of them. So for problems like this, so this is a nasty issue with amines. So if we have R in H2 and we add Rx, R prime X, we expect this to keep removing the halogens, and so we get plus X, plus 2X, plus 3X. And the question is, do we need to worry ourselves with, also NH4 is in there too. Do we have to write all of them? The trick here, and we typically see this, what the textbook will do, what I will do, is that you put a number here. And the number dictates the number of times that it's going to do this type of substitution. So if there's only 1 here, you'll get this product. If there's a 2 here, you'll get this product. If there's a 3 here, you get 3 here. So basically the number here needs to match the number in front of whatever is attached to X. All right, Hoffman reaction. So if there is a hydrogen present on less substitute carbon, will it get removed from there only? So I think the question being asked is, so the example in the notes is this. So we've done this reaction, and now we're going to add silver 1 oxide to it, and we should get a terminal alkene. But let's say we had this molecule here. Does the elimination go here or here? And the answer is going to be down here, and it's just sterics. So if we end up having our amine on like a secondary and we do elimination, we have a choice of carbons to go with, we're going to go with a less sterically hindered carbon. And this is pretty typical of these silver 1 reactions. There's something like a Fedazone oxidation. There's a lot of details that are kind of left out of the reaction that are really super important. This tends to have a lot of stereochemistry associated. So particularly with the silver 1 reactions, there's a lot of stereochemistry associated with those. And so typically you're doing this in order to, you're going to end up doing terminal eliminations because they're the ones that reduce the steric hindrance of the reaction. And this is also part of the reason, okay, we're not going to get the Fedazone oxidations. But yeah, the answer is that if you have a choice, you're going to go with the least sterically hindered carbon for the one that removes the hydrogen. If there's only a tertiary, will you remove it? The tertiary doesn't have any hydrogens to remove, so if you had this, you would have no reaction. So nothing would happen in this case. You would just end up with the ammonium salt. Yes, the reason why we like the Hoffman elimination, it is basically the anti-Zaitsev equivalent. Instead of eliminating from the most substitute carbons, it eliminates from the least substitute carbons. And there is power to that. Sometimes you do want to put an alkene on the end, and it's just, this amine chemistry is pretty straightforward for that. All right, next question. Microreaction decarboxylation. I think when I wrote the key, I was getting a little overzealous here. So it's this reaction here. And the key has it written out as this for the Michael reaction. And I don't agree with it. I think I was looking at a different problem when I wrote it. So the Michael reaction, the easiest way to think about it is just an HX addition. Honestly, I should go back and update a lot of these because the Robinson annulation is the addition and elimination. Anyway, so what's going to happen with a Michael reaction is that we're going to do an HX addition. And this is going to add to here. Let me check the notes really quick to make sure I'm right before I start pontificating about something I'm not correct on. Okay, so yeah, all the answers are actually incorrect in the key. Um, what you're seeing written with the microproduct is actually the Robinson annulation product. It is not the microproduct. The microproduct is simply addition to that double bond. So I need to go back and update the key. So the microproduct here, this is our X. We're going to do an H, X addition across the bond. And we're going to end up with this. And then the Robinson annulation is when you get an attack of a carbonyl carbon. So we have 1, 2, 3, 4. That's actually too close. Yes, that's too close. 1, 2, 3, 4, 5, 6. So we'll get an attack of this carbon onto this carbon, and this will get us our 6-membered ring. So we've got 1, 2, 3, 4, 5, 6. Carbon 1 is attached to carbon 6. Carbon 6 is the alcohol, the bond. Carbon 5 has this group hanging off of it. Carbon 4 attached to carbon 5 are good. 3, 2. And then we would get subsequent elimination. To get this. So yeah, the keys are actually wrong on this. That's kind of embarrassing. So the microproduct is only the addition across the double bond. The annulation is what happens when the alpha carbon attacks and forms that 6-membered ring. So I just need to go back and correct the key on this one. It probably take, unfortunately, I'm not going to have this done by tomorrow. I guess I could. I'll try to have this updated key posted by Wednesday, but that's going to be a challenge. Yeah, the key is only showing the Robinson annulation addition elimination products. So mercifully, I don't have to correct those, but yeah, the Michael products aren't incorrect. Those are just HX additions. Which is weird because they're correct to the decarboxylation ones. Who knows what I was doing. So yes, for the microreaction decarboxylation, those microproducts are all correct. Just taking a quick skim at them. It's the Robinson annulation I got overzealous and didn't list the microproduct. What I listed was the Robinson annulation product if you did for the initial step, not when you get the dehydration. Okay, luckily not to correct all of them. So you're always going to favor a 6-membered over a 5 over a 4. And this is why when we write the annulation product, I don't even bother starting here with the 1, 2, 3, 4 product. A cyclobutane ring can be formed, but these are pretty big groups. So yeah, you might be able to isolate some cyclobutane product, but you're definitely, if you can form a 6-member ring, you will, and this is kind of why Robinson annulation is a thing. That because this formation of a 6-membered ring is so stable, you're pretty much guaranteed to get this product. But always the 6-membered ring is the more favored product. Can you work through problem 2 on page 13 as well? Yes. Yeah. Okay, this monstrosity. That should be a CH2 group. That should be a... That's supposed to be your ketone. Oops, typo. And we've got our favorite microreagent. So this is going to attack, and we're going to end up generating as our microproduct 1, 2, 3. This product. So this is the first, this is the actual microproduct. And then the Robinson annulation. 1, 2, 3, 4. Hold on. Did I draw it wrong? Oh man, okay, that structure's wrong. It should actually be, the double bond should be there. Man, that's a nasty typo. So the double bond's in the wrong place, and that should be an option. So now if you do this, 1, 2, 3, 4, 5, 6. This is going to attack here to give us our 6-membered ring. 5, 6. And okay. So we've got carbon 6 attached to carbon 1. Carbon 1 has our OH. Carbon 2 has that hanging off. 3 has that. 4, 5, and 6. And then we'll most likely do the elimination to get that. So there's your microproduct, and there's your Robinson annulation product. Page 8, problem 3. You're overthinking it. So I agree with the key. The key, yeah, you're just overthinking it. So if you look at this reaction, you look at the key, and you might say, well, this looks like the aldehyde attacked here. If you take this structure and you just turn this methyl group down, this will attack and give you this structure. So this is the actually that starting 5-membered ring. But it's just drawn differently. So what happened here is it just turned the methyl group down, and then that attacked the aldehyde. Page 5. Page 8, 3. Yeah, I've updated the key. Actually, it'll give you the same one both times. So if you look at the H2OCl2, and it will actually hydrolyze and react with the Cl. So you end up getting the same answer, but for different reasons. So if we do the keto form, or the enol form, if we do H2OCl2, you'll end up, this ends up being the more positive carbon, which is where the hydroxide is going to attack. And so you end up getting Cl added here, and the diol if you start with this, you also get the water to add to the double bond. Sorry, it's pretty poorly drawn. So this will add to the double bond, and because this carbon is acidic, it will attack the Cl. So you actually end up getting the same answer, but for different reasons. For this one, this is just halohydrogen addition. This is actually two reactions. This is the hydration of the ketone and substitution of that acidic carbon. So yes, you end up actually getting the same answer, but it's for like radically different reasons. It's an interesting problem. It'd be worth discussing. All right, you're welcome. I need to start up a different computer. I'll be right back. Can you go over which is more stable for the enols versus the ketone form? So let's say we have our generic ketone and we're going to tautomerize it to our enol. And the question is, which is more stable? And so just an isolated enol is not stable. It will act like an enol underneath highly acidic or basic conditions when you kind of favor that hydrogen transfer, but generally speaking, this is just not a predominant form. We can make it more stable, it will create conjugation. So if R here have double bonds that are conjugated, and adding this conjugated group in here, so let's say R here is this. By creating conjugation, you inherently stabilize the material, particularly if that conjugation, actually is a bad example, if the conjugation is away from the ketone group. So here we've completely isolated, and the reason why it's not a good example if I put the double bond here, the double bond here is already conjugated with that oxygen, but definitely if making that double bond puts another double bond in conjugation with others, that makes it more stable. The ultimate end result of conjugation, though, the best form of conjugation is aromaticity. So if we end up generating an aromatic molecule as a result of the tautomerization, we will end up generating the enol form because aromaticity is one of the most stable forms of organic molecule. So if we consider something like a diphenol, we can convert this to the ketone form through tautomerization. Sorry, I'm running out of board space here. But in doing this, first time we do it, we break aromaticity. Second time, we break conjugation. So we create two isolated ketones that are nowhere near a double bond. So the first time, if you were to make this molecule, the first time you exchange a hydrogen, the favorability for the enol would be higher because now you've created 1, 2, 3 conjugated double bonds. Now, tautomerizing this one will end up generating an aromatic benzene ring, so that makes it the most stable form. Again, turn on. So something like a Grignard attacked a double bond next to a ketone aldehyde, would it just stop there or would it do further reactions? So generally speaking, they're going to want to go for that carbonyl. So if you do get addition to that double bond, so let's do this. And let's say you had your RMGBR and it attacked here. So what's kind of stabilizing this one right here is this conjugation. And let's say instead of going for this, it attacked this first. Well, now we have a problem. So if we have a hydrogen source here, so okay, first of all, if we had a hydrogen source, we would react with our Grignards. But the second issue is, in principle, this could also attack. You could have a further attack here on the ketone. So now that you've broken up this conjugation, there's a proclivity here now to attack that double bond as well. So the Grignard is going to have issues of subsequent attacks on the ketones. The Michael reagent is so big, it doesn't really facilitate that or let that happen. All right, I actually need to take off for my PD session to get set for that. So again, if you ever have questions, these are not lessons, these are not lectures, these are just office hours, but I do enjoy it when you'll actually send questions in advance. So I will see some of you for lab tomorrow, and good luck on your exam this week, and I'll see y'all next week.